Today we are going to talk about linear momentum, and we are going to talk about impulse and momentum. Impulse is the product of force and time which take place at a short time, while the momentum is the product of the mass and the velocity of that object. When a ball is hit by a force of 50 Newton for a time of 0.03 seconds, the impulse is force times time, and that is 50 Newton times 0.03 seconds, and that gives us 1.5 Newton seconds. Example 2. A body of mass 3.0 kg moving with a velocity of 10 meters per second. Find the momentum. The momentum is mass times velocity, and that is 3.0 kg times 10 meters per second. That gives us 30 kg per meter per second. 30 kg per second. Newton's laws of motion. The first law says every object will stay in a state of rest unless acted upon by an external force. If you place your phone on your desk for 1 hour, 2 hours, it will still stay at the same place unless acted upon by an external force. What is the external force? Vibration is also an external force. When you move it away from that place, it's an external force. The second law of motion states the time rate of change in momentum is proportional to the applied force and take place in the direction of that force. Third law says to every action there is equal and opposite reaction. This takes us to rockets. When you look at rockets, we see that the rate and speed at which the rocket expels the gas, the rate at which the rocket moves upward. So we'll go to example of momentum. Let's solve some example. A body of mass 0.3 kg moves at a velocity of 20 meters per second. It's suddenly hit by a force of 5 Newton for a time of 0.3 seconds. Find the new velocity. Firstly, we know that the impulse equals the change in momentum. And from the question, we have given the force, which is 5 Newton, the time, which is 0.03 seconds, the mass, which is 0.3 kg, and the velocity, the initial velocity, which is 20 meters per second. We are asked to find the final velocity. So our impulse is force times time, that is 5 times 0.03, that gives us 0.15, equals change in momentum. And from change in momentum, the mass is the same. Then we can factorize the mass from the equation. So mass, when you factorize the mass, that is V minus 20. Then 0.15, which is the impulse, equals 0.3, the mass, into bracket V minus the initial velocity, which is 20. Divide both sides by 0.3, and that gives us 0.15 over 0.3, that gives us 0.5, equals V minus 20. Then the final velocity now is, take that 20 back to the other side, and that is V final velocity equals 0.5 plus 20, and that gives us 20.5 meters per second. That is our final velocity. We are moving forward to conservation of linear momentum. The conservation of linear momentum says in a closed system, the total momentum after the collision is equal to the total momentum before the collision. For example, a bullet of mass 0.05 kg is fired horizontally into a 10 kg block, which is free to move. That means that block is a stationary point. They both move with 0.5 meters per second after impact. They both move with the same velocity after impact. Find the velocity of the bullet before impact. The initial velocity of the bullet, that what we are going to find. Then, from our laws of conservation of linear momentum states the linear momentum, total momentum before the collision equals the total momentum after the collision. Then m1 and u1, the m of the bullet and u, initial velocity of the bullet, plus the mass of the block and the initial velocity of the block equals the mass of the block plus the mass of the bullet into bracket the velocity at which both move. Then that is 0.05 times the initial velocity of the block plus 10 times 0 equals m1 v1 plus m2 v2. And the answer is 100.5 meters per second. Collision is divided into elastic collision and inelastic collision. In elastic collision, both the momentum and the kinetic energy are conserved. But in inelastic collision, only the momentum is conserved. Application of linear momentum. First is recoil of a gas. A gun has a backward momentum equal to the momentum of the bullet. When you fire the bullet, then that speed at which the bullet moves from the gun is the same speed, that's a backward effect, at which the gun will move backward. Also, jet and rocket propulsion. As rocket hot gas is expelled downward at high speed, an equal and opposite force momentum is given to the rocket, which sets it to move upward. Walking. The ground exerts an equal and opposite force back on the person, moves the person forward. The ground exerts an equal and opposite force which moves the person forward. Then we are moving to inertia, mass, and velocity. Inertia is the reluctance force or resistance to a change of state of momentum. This is the force that is hindering us of moving. This is a force that must be overcome before an object can move, can tend to move. That is it. And what is weight? Weight is the force acting on the body due to the effect of gravity, due to the Earth's gravitational pull. And this force is higher at the pole and lesser at the equator. The mass is the measure of the inertia of the body. The greater the inertia, the greater the mass. The greater the mass, the greater the force that is required to cause it to tend to move. Change in momentum. Mass is always constant, while weight varies, because at the polar axis, the weight is higher, while at the equator axis, equator pole, the weight is lesser. Mass is measured with chemical and beam balance, while weight is measured with spring balance. Let's look at weight in lift. Weight in lift. When elevator is stationary or move with a constant velocity, the acceleration is 0. Then the weight equals the reaction force acting in that lift. So when the lift accelerates upward, then the reaction force that is mentioned by the spring balance equals the force of the acceleration and the weight of that man, and that gives us ma plus mg. When the lift decelerates, as it's decelerating, that force is small, so the reaction force will equals the weight minus the deceleration force. So that gives us R equals mg minus ma. Also, when it is falling freely, when a weight is falling freely in a lift, the acceleration equals the gravity, and then the man is weightless. It has no weight. There's zero resistance force acting because R, which is equals mg minus ma, equals 0. So there is no weight. That person is weightless. We also talk about satellites and weightlessness. People orbiting space close to the Earth experience weightlessness, which is same with freely falling elevator. An aircraft of mass 2.5 kg times 10 raised power 5 kg traveling at 500 meters per second. Find momentum. What is the momentum? Momentum is mass times velocity, and that is 2.5 times 10 raised power 5 times 500 meters per second, and that gives us 1.25 times 10 raised power 8 kilogram meter per second, and that is our momentum. To the second question. A constant force of 5 Newton acts for 5 seconds on 5 kg mass at rest. Find the momentum. We know that the impulse equals change momentum, and our impulse is force times time, which equals our m1 v1 minus m2 v2. That is momentum of the final velocity minus the momentum of the initial velocity, and that is 5 times 5 for the impulse, which gives us 25, and for our momentum, that is 5 times v minus 5 times 0, because it is at rest, and that is 25 over 5 equals v. Our v now is 5 meters per second. Sorry for not putting it there. Never forget to put units to your solution. Another question says, a tractor of mass 5.0 times 10 raised power 3 kg is used to tow a car of mass 2.5 times 10 raised power 3. The tractor moved with a speed of 3.0 meters per second. Just before the rope was towed, calculate the speed of the tractor immediately the rope became taut. Solution. From the diagram, you see I drill before taut the upper one and the straight one in the middle. That is when it is taut. So when the tractor which want to drive a car, the rope must become taut before the car begin to move. So the car initial velocity is 0 because it's at a state, it's not moving. Why the tractor? The tractor, they have already given us the speed, which is 3.0 meter per second. That is the speed of the tractor, the initial speed of the tractor. So this tractor has to move with the speed of 3.0 meter per second before this car tends to move. It's not that the car has already started to move. It tends to move before it's about to move. That is it. So using our laws of momentum, which says momentum before collision equals momentum after collision, and that is m of car times the u of our car plus m of tractor times the u of our tractor equals m of our tractor times the final velocity of our tractor plus m of our car times the final velocity of our car. The first question states speed of the tractor immediately will become that. So the initial velocity is 0. That's why we have 2.5 times 10 raised to power 3 times 0 plus the mass of the tractor, that is 5 times 10 raised to power 3 times the speed, the initial velocity of the tractor, which is 3 meter per second, equals, since we are dealing with inelastic momentum, the final velocity of both will be the same. So we can factorize the mass. So we can factorize the velocity. When we factorize the velocity and we add the mass together, the mass equals 7.5 times 10 raised to power 3. With our initial momentums, when we add them together, that is 0.0 plus 15 times 10 raised to power 3, and that gives us 15 times 10 raised to power 3. So we now want to get our final velocity, which is the total velocity of both the tractor and the car. Then you have to divide both sides by 7.5 times 10 raised to power 3, and that is 15 times 10 raised to power 3 over 7.5 times 10 raised to power 3. And when we divide that, we get 2. And then our final velocity, which is the same thing as the velocity of the tractor and the velocity of the car, is 2 meters per second. Question 2 is loss in kinetic energy just after the car has started moving. Let's look at the solution. We group it into before collision and after collision. Before collision, don't forget that it is inelastic momentum, and therefore the kinetic energy before collision now does not equal to kinetic energy after collision. So they want to know the difference. That's what they know about the loss of kinetic energy. So half mu square plus half mu square for car and for tractor. So that's before collision. We know the mass of the car and others, so we have to apply them. Half times 2.5 times 10 raised to power 3 times 0 for the first one. The initial velocity of the car is 0. For the tractor, half times 5 times 10 raised to power 3, which is the mass of the tractor, times 3, which is the velocity. And we know that it is velocity square, so 3 raised to power 2. And then we get 0 plus 7.5 times 10 raised to power 3 times 3. And our answer is 22.5 times 10 raised to power 3 joules. After collision, half mass of the car times velocity of the car plus mt, which is mass of the tractor times velocity of the tractor raised to power 2, half into brackets mc plus mt times velocity, because the velocity is the same thing. Then we factorize the velocity out. So like we factorize in when we are dealing with momentum, linear in the momentum. So we apply the same thing here. So half times 2.5 times 10 raised power 3, add the mass together, times the velocity, which is 2 raised power 2. Then we get 50 times 10 raised power 3 joules. Our loss in energies now is the energy before collision minus the energy after collision. That is 22.5 times 10 raised power 3 minus 15 times 10 raised power 3. And then we get 7.5 times 10 raised power 3 joules. That is our loss in kinetic energy. The third question says, find the impulse in the rope when the car jacks into motion. The impulse is what? Change in momentum. So we are talking about the change in momentum of the car. So the momentum before collision is mc times initial velocity, and that is 2.5 times 10 raised power 3 times 0. Give us 0. After collision, we have mc times final velocity. That is 2.5 times 10 raised power 3 times 2 equals 5 times 10 raised power 3 kilogram meter per second. That is our answer. So what is now the change in momentum? Subtract it, 5 times 10 raised power 3 minus 0 equals 5 times 10 raised power 3 kilogram meter per second. So, or you call it Newton seconds. That's why I say you should note it. It's the same thing as that. This is the end of our today's lesson. We hope that you learned some things from today's lesson, and we're going to drift back to what we have learned from the linear momentum, which is impulse and momentum, Newton's laws, conservation of laws of linear momentum, elastic and inelastic. I want to put something there. Elasticity, the example of elastic is ping pong ball, tennis ball. When you play it to the wall, it returns back to you. That is elastic. Application of elasticity, when we talk about working, recoil of the gun, rocket propulsion, inertial mass and weight. When we talk about inertial force that gives us to be stable at a place, the mass, which is the quantity of inertia that we contain in our body, the weight, which is the force of gravity on a body to earth, the weight in elevator and weightlessness. We hope you enjoy the examples. If anything is not clear, please leave a comment. We are going to attend to it. We urge you to subscribe to this channel. I pray that God bless you as you do so. If you like the video, leave a like, comment in the comment section, so I'm going to know what to work on. Thank you very much.